Now we will be discussing the previous year GATE questions from irrigation engineering. So I have divided the full topics into different chapters, which is water requirement of crops, stable channels, seepage, spillways and gravity dam. So we'll see the first question. The delta in centimeter, duty D in hectares and base period in days are related as. So as we know, delta is equal to 8.64 B by D. This is B by D. This is when the base period is in days, duty is in hectare per cubic, delta is in meters. Now they have asked delta in centimeters. So if you have to get delta in centimeter, we have to multiply this by 100. So it will be 864 B by D, where delta is in centimeter. So the answer will be A, delta is equal to 864 B by D. Next question. If duty is 1428 hectares per cubic, that is duty value is given as 1428 hectare per cubic and base period B is given as 120 days for an irrigated crop, then the delta in meters is given by. So delta in meters is given by 8.64 B by D. So if we substitute 8.64 into B is 120 by D is 1428, then we will get the value of delta in meters as 0.73 meters. So delta is given by 8.64 B by D. The answer will come out to be 0.73 meters. So answer will be B. Next question. A tube well having a capacity of 4 meter cube per hour. Okay, there is a tube well and the capacity, that is it can discharge, or the output discharge is 4 meter cube per hour and it operates for 20 hours each day. On one day it operates for 20 hours during the irrigation season. That is, during the irrigation season means during the base period. How much area can be commanded if the irrigation interval is 20 days and the depth of irrigation is 7 meters? Okay, irrigation interval is given as 20 days and depth of irrigation is 7 centimeter. We have to find out the area which can be commanded. So we know that area is equal to the volume divided by the depth, or we can write it is equal to the volume divided by depth of irrigation. Depth of irrigation here it is given 7 centimeter. Now we have to find out the volume of water which is supplied to that area. So for finding out the volume, it is given that tube well has a capacity of 4 meter cube per hour. Okay, that is the capacity of the tube well. Now that tube well is operating for how many hours? It is operating for 20 hours. Now it is operating for 20 hours per day. On one day it is operating for 20 hours. Okay, and what else is given? Each day during the irrigation season, that is during the irrigation period, it is operating at this date, and it is the irrigation interval is 20 days. For 20 days a tube well is running which has a capacity of 4 meter cube per hour and it is running for 20 hours on each day. So once you solve this, we will get the value of volume, that is 4 into 20 into 20 meter cube, or the volume is equal to 1600 meter cube. Okay, now we know the volume of water which is supplied to the irrigation field. Now how can we find out the area? Area will be equal to 1600 meter cube of volume divided by 7 by 100 centimeters. So if I solve this, I will get the value of area to be approximately the value option D, that is 2.29 into 10 raised to 4 meters square will be the value of the area. Okay, we'll see the next question. That is, a field was supplied water from an irrigation tank at a rate of 120 liters per second to irrigate an area of 2.5 hectares. Okay, this is the rate at which the water is supplied and area to be irrigated is 2.5 hectares. The duration of irrigation is 8 hours. We are operating or we are supplying irrigation water for a period of 8 hours. It was found that the actual delivery at the field, which is about 4 km from the tank, was 100 liters per second. Okay, so there is a tank, and from this tank we are supplying water to a field. So from the irrigation tank water is flowing at a rate of 120 liter per second, and the area of this field is 2.5 hectares, and the time is 8 hours. It was found that the actual delivery of the field, which is the distance is 4 km, and actual delivery was 100 liters per second. And also after delivering to the field, there is some loss of water from the field because some water will be lost as runoff, and the loss of water and the form of runoff is also given. It is 800 meter cube. Now we have to find out the application efficiency in this case. So we know that the water application efficiency is given by the water stored in the root zone. Water application efficiency is water stored in the root zone during irrigation. Water stored in the root zone during irrigation to the water delivered to the field. Into 100. So the formula for water application efficiency is this. Now we'll see how to solve this question. So here, what is the water delivered to the field? Water is delivered to the field. The water delivered to the field is at the rate of 100 liters per second, and it is supplied for 8 hours. So 8 hours, which is equal to 8 into 60 into 60 seconds. So this is the volume of water which is delivered to the field. Okay, and what is the water stored in the root zone during irrigation? By solving this, you will get 2880 meter cube. So this much water is getting delivered into the field. From this tank, water coming is 2880 meter cube, and there is some runoff loss of 800 meter cube. So what is the water stored in the root zone? It will be 2880 minus 800, or I can say this term will be 2080 meter cube. Okay, so water application efficiency will be given by 2080 by 2880 into 100, and the answer will come out to be 72%. So in this question, this 120 liter per second is an extra data. That is the rate which is supplied from the irrigation tank. But we for water application efficiency, we will consider the rate of water which is supplied to the field. So water is supplied to the field at the rate of 100 liters per second. That is why we used 100 liters per second here, and it is supplied for 8 days. Okay, so that answer will be B, 72%. Next question. A canal was designed to supply the irrigation needs of 1200 hectares of land growing rice. So there is the area is given as 1200 hectares, and for a growing rice of base period is 140 days, having delta of 134 centimeters. Okay, so there is an canal. We are given the area, base period and delta. Okay, for rice. Now if this canal water is used to irrigate wheat, now the same canal water is used to irrigate wheat, and the base period of wheat is 120 days and delta is 52 centimeter, then the area which can be irrigated. So what is the area which can be irrigated for wheat? It is, we are using the same amount of discharge as required for rice, but here the base period and delta is different. So how much area can we irrigate using the same discharge? So that is the question. We will see the answer. So discharge is given by area into delta by base period. Okay, so or I can say that delta is equal to 8.64 B by D, and also we know that discharge duty is equal to area by Q. So from that we will ultimately get the value of Q. That is, from this equation I know that Q is equal to A by D, and D I can write as, from this equation D will be equal to 8.64 B by delta. D will be equal to 8.64 B by delta, or I can since this 8.64 is a constant value, and if I equate both the discharges, this 8.64 term will get cancelled. So that is why area is discharge is written as area into delta by base period. That is, here we are equating the discharge of the both the crops. Okay, so it is especially mentioned that if this canal water is used, which means the same discharge is used. So discharge of both the cases is same. So area into delta by base period, that is area of the first rice crop is 1200 into 134 is the delta, and divided by the base period is equal to area of wheat crop, which we have to find out, into delta of the wheat crop is 52 centimeter and base period is 120, and once we solve, the answer will be 2650 hectares. Okay, so answer is A, 2650 hectares. Next question. The total irrigation depth of water required by a certain crop in its entire growing period is 25.92 centimeters. Okay, that is entire growing period, base period is given as 150 days and irrigation depth is 25.92 centimeters. The culturable commanded area for a distributary channel is 100,000 hectares. The distributary channel shall be designed for a discharge. We have to find out the discharge. Now we know that delta is equal to 8.64 B by D. Here delta is 25.92 in centimeter. In meter it will be divided by 100. Is equal to 8.64 into B is 150 divided by D. So from there we will get the value of duty. Now again duty is equal to area by discharge. So discharge will be equal to area, that is 100,000 hectares divided by the value of duty from here. So the value of duty will be 5,000 hectares per cumex from by solving this equation. So we will find out the discharge. So the discharge will be equal to 20 cumex. Okay, discharge will be equal to 20 cumex. So this is the discharge which is required for the plant. but when we are designing a canal, always it should be for more than 20. If the requirement of the plant at the field is 20 cumecs, means the channel should be able to carry more discharge. Only if it carries more than 20, only if it carries 25 or something, then after all the losses we will be able to deliver 20 at the field. So it should be designed for a discharge which will be equal to more than 20 cumecs. Okay, so the answer will be D, more than 20 cumecs. Okay, next question. The moisture content of the soil in the root zone of an agricultural crop at certain stage is found to be 0.05. Okay, at some particular stage the moisture content is 0.05. This is the moisture content in the plant. Now the field capacity is also given. This value is the field capacity. The root zone depth. What is the root zone depth? Root zone depth is small d. It is 1.1 meter. The consumptive use of crop, that is CU. Consumptive use means CU is also given, and there is no precipitation during this period. Irrigation efficiency is 65%. Efficiency of irrigation is 65%. It is intended to raise the moisture content to the field capacity in 8 days through irrigation. Okay, that is we are providing irrigation, and the presently the moisture content is 0.05, and we are increasing it to the field capacity in how many days? In 8 days. So now we have to find out the necessary depth of irrigation, or we can say we have to find out the depth of water to be applied. Okay, so we'll see this question in detail. That is, since we have been given the presently the moisture content is 0.05 and field capacity is 0.15. Dry density is given, and depth of root zone, consumptive use for 8 days, and efficiency is given. Okay, now we will see how to solve this question. We know that the depth of water is given by gamma D by gamma W into D into the field capacity minus the moisture content. Okay, that is here usually we take optimum moisture content, but in this case presently the moisture content is this particular value of 0.05. Now we have to increase it from this value to the field capacity by supplying water. So if we take the difference of field capacity and the moisture content, we will get the depth of water corresponding to the difference of those two. So we have to find out gamma W. Here gamma D is 1.5, gamma W is 1, depth of root zone is 1.1, and field capacity is 0.15 minus 0.05. So from here I will get the depth of water as 0.165 meters. Okay, now also the consumptive use is given as 2.5 millimeters per day. For how many days? For 8 days. That is, for 8 days the consumptive use is at the rate of 2.5 millimeters it is using for 1 day. Okay, so the total consumptive use will come out to be 0.02. It will be in meters. Okay, 0.02 meters. Again we have to find out what is the depth of water or irrigation water to be supplied, because here in this question the efficiency of irrigation is given as 65%. Now the efficiency of irrigation is always output by input. Okay, now it is given efficiency is 65%, and what is the output? That is, when we supply irrigation water, what is the output? We are supplying irrigation water to meet the needs of the plants. So in this case, the consumptive use of requirement of water is 0.02, and the depth of water required to increase the moisture content from this present moisture level to field capacity is this. So this does not include the consumptive use requirements. So the total requirement at the field will be sum of these two, or I can say that it will be 0.185 meters, okay, divided by the input. So that is the water input, means the water should be carried by the canal or the irrigation water to be supplied. So this is what we have to find out, and once we solve this equation, we will get the value of this question. The answer will be 285 millimeters. So in millimeters, the value will be equal to 285 millimeters, which will come out to be 285 millimeters. Okay, so remember that in this depth of water requirement, the consumptive use is not included. That is why the total requirement of the irrigation water at the field or at the output, we have to get 0.185, which is sum of these two. And since irrigation efficiency is only 65%, okay, that is if we supply 100, we will get only 65. So to get 0.185, we should actually supply more than that, and that is equal to 285 millimeters. Okay, so that is the answer to this question. Next question. A sprinkler irrigation system is suitable when the land gradient is steep and the soil is easily erodible, or the soil is having low permeability, or the water table is low, or the crops to be grown have deep roots. So sprinkler irrigation is used in the first case, that is when the land gradient is steep, and if the land gradient is highly sloping or steep, then if we provide irrigation by other methods such as furrow irrigation or flooding irrigation methods, the water will easily flow down to the downstream end. So if we provide water irrigation by means of sprinkler method, then the water will be easily absorbed by the into the root or into the soil, and there will be minimum wastage of water due to the slope. So the answer to this question is A. Okay, next question. A canal irrigates a portion of a culturable commanded area to grow sugarcane and wheat. Okay, so there is a area where we grow both sugarcane and wheat. Okay, the average discharge required to grow sugarcane and wheat are respectively. So the discharge required for we have sugarcane and wheat. The discharge required for sugarcane and wheat are 0.36 and 0.27 cumex. Time factor is 0.9. Okay, time factor is given as 0.9, and the required design capacity of the canal is. Okay, now we'll see about time factor. So time factor is actually the ratio of the actual operating period to the crop period, which means actually we require irrigation for the plants during the crop period or the base period. Okay, if this is the let us say it is 100 days, this is the crop period. Okay, during this crop period we require irrigation, but we do not supply irrigation on all these 100 days. We supply irrigation intermittently or at some intervals. Let us say for the first 3 days I supplied irrigation water, then afterwards the moisture content in the soil will reduce, it will become that optimum moisture content. Again we have to supply irrigation after some days. So let us say that out of the 100 days, which is the crop period, we are actually providing irrigation. Actual operating period is let us say 9 days. Okay, for example, if it is 9, so this time factor will be 9 by 100. So we can see that always this time factor will be less than 1, because the actual operating period is always less than the crop period. Okay, now there is another equation, that is the design discharge into time factor will be equal to the discharge required. Okay, because I said that time factor is always less than 1, and we know that we always design for a greater discharge than what is required. So only if this value is high value into a value less than 1, we will get the required design discharge. Okay, so remember this formula, that is design discharge into time factor will be the required discharge. Now in this case we have to find the design discharge. So design discharge will be the Q required divided by the time factor. In this case we are growing sugarcane and wheat. So sugarcane is a perennial crop, that is it is grown throughout the year, and wheat is a rabi crop. So both will overlap, that is sugarcane is for 365 days and wheat is grown in between somewhere in the rabi season. So at any particular time, if I consider this particular time, the discharge requirement will be the sum of both these two. So the total discharge required will be 0.36 plus 0.27 divided by the time factor, which is 0.9. So by solving this, we will get the value of the design discharge as 0.70 cumex. Okay, this will be the value of the design discharge. Next question. The culturable commanded area for a distributary, culturable commanded area is given as 2 into 10 power 8 meters square, and the intensity of irrigation for a crop. So for a crop, the intensity of irrigation is given, that is the area on which a particular crop is cultivated is 40% of this value. Okay, 40% of this value, and this will come out to be 8,000 hectares. Okay, this conversion is 1 hectare is equal to 10 power 4 meter square. Okay, by converting into hectares, it will be 8,000 hectares. Now, if the core water depth and core period, core water depth is similar to delta, it is we have discussed in the theory, core water depth and core period is 14 centimeters and 4 weeks. Always remember that the base period should be in days, so it will be 4 into 7, that is 28 days. Okay, then we have to find out the peak demand discharge. We have to find out value of Q. We know that duty is equal to area by discharge. So discharge is equal to area by duty. We know the value of area. We have to find out duty using the equation delta is equal to 8.64 B by D. From that, find out the value of duty. Okay. So after solving, you will get the value of the discharge. The discharge value will be equal to 4.63 meter cube per second.